Hello again. This is Math 2134 coming to you from the College YouTube page, and the title of this lecture is More Derivatives. We're going to talk about the chain rule for exponential functions. We're going to talk about taking the derivatives and the chain rule for logarithms. And we're going to talk about derivatives of exponential and logarithm functions with other bases in this lecture. Now, you recall that the derivative of e to the x with respect to x is e to the x, so that means we'll combine this with the chain rule, which says that the derivative with respect to x of y is, so dy dx is equal to dy du times du dx. So the derivative with respect to x of e to the u, where u is a function of x, is e to the u times du dx. This says the same thing. Let's do three examples here. In the first one, u is equal to 2x. In the second one, u is equal to minus 3x. In the third, u is equal to 2t squared plus 1. So what we will do then is the derivative of f then is going to be e to the u times du dx, which is going to end up being 2e to the 2x. Here, u is minus 3x, so it's going to be e to the u times the derivative of minus 3x, which is minus 3. And here, the u is more complicated, but the derivative is going to be e to the u times the derivative with respect to t of what was the exponent, and that's going to end up being 4t plus 1, e to the t squared plus 1. We also can apply this when we have products. So here we have the product of two differentiable functions of x. X is the first function, and the second function is e to the minus 2x. So we're going to use the chain rule, and we have to use the we're going to use the product rule, and then we have to use the chain rule. So what we find is the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first. Now the derivative of x with respect to x is just going to be 1. We don't even need to write that. But here what we're going to do is we're going to have to take the derivative of this. And the derivative of this is going to be e to the minus 2x times the derivative of this, which is minus 2. And so when I simplify, I get this. And simplifying further, I can factor out the e to the minus 2x. There are situations where we will want to do this factoring as we go into higher chapters in order to solve the problems. It also works for quotients. Here we have a numerator and a denominator and g of t. And you might say, I don't see a chain rule. Well, I do, because what happens here is that we've got e to the minus t, not just e to the t, so there's a chain rule going on here. So we're going to use the quotient rule. So g prime of t is going to be the denominator times the derivative of the numerator minus numerator times derivative of the denominator, all divided by the denominator whole squared. So you see this is just this, the derivative of e to the t with respect to t is e to the t, and the derivative of this with respect to t is going to be e to the t, but then it's going to be minus e to the minus t because of the chain rule. And then we can multiply this out and do some simplification. And we see that in this case, when we simplify things, the e to the 2t and minus e to the 2t cancel out. So the answer is 2 over e to the t plus e to the minus t whole squared. Many exponentials arise in applications, and so a common equation in science is that q of t is equal to q0, an initial amount, times e to the kt. And so what this is saying is show that for a quantity q of t experiencing exponential growth, the rate of growth of the quantity q prime of t, because the derivative always is the rate of growth, at any time is directly proportional to the amount of quantity present. Well, you see this is what q of t is, so when you take the derivative, q prime is going to be, this constant just sits there, and then you're going to take the derivative of e to the kt. So that is going to be e to the u times the derivative with respect to t of u, that becomes k. So you see q prime of t is k times, And what this is actually still q of t. So that says that q prime of t is directly proportional to q of t, which is the desired conclusion. Let's find the first and second derivatives for the function y equals f of x equal e to the minus x squared. So the first derivative, u, is going to be minus x squared, so the derivative is going to be e to the u times minus 2x. But now we're going to take the second derivative, and now when we take the derivative yet again for the second derivative, the minus 2 is just going to be sitting there, or we'll pull it through, but we're taking a product now. This is going to be x times e to the minus x squared, so it's going to be the first times the derivative of the second. You see the chain rule happening here because the derivative of minus x squared is minus 2x, and then it is going to be, this is the first times the derivative of the second, and that minus 2 is being distributed, and so we take the derivative of the first, which is x. That's just going to be a 1, and this is e to the minus x squared, and again we can factor out the e to the minus x squared out of this. And you remember the exponential is never 0, so this is going to be useful later on as we solve problems to do this factorization. Okay, now we're going to change gears, and we're going to talk a little bit about logarithms. And we're going to be using implicit differentiation to do this. So, whenever we say y is equal to f of x is equal to the natural logarithm of x, if I write that in exponential form, that says that x is equal to e to the f of x. So that means what we can do is we can use implicit differentiation and the chain rule here. So I do that. I take the derivative of both sides. The derivative of x with respect to x is 1. The derivative of e to the u is e to the u times du dx, or f prime of x. So that means f prime of x, when I solve for it, it is 1 over e to the f of x. I just divide both sides of this by e to the f of x. That's never 0. But since e to the f of x is equal to x, that means I can substitute, and this is f prime of x is equal to 1 over x. Okay, so that's what we sort of set out to show. Now let's summarize that by saying the derivative of the natural logarithm of x is 1 over x, for x not equal to 0. And thinking about the chain rule then, the derivative with respect to x of the natural logarithm of u is going to be 1 over u times du dx. Again, these are formulas you are committing to memory. So let's do some examples. In the first one, we're saying the natural logarithm of u, and u is 2x, so it's going to be 1 over u times du dx. So what we get is 1 over 2x, and then du dx is 2. And so the 2's cancel, so I get 1 over x for that. In problem B, I'm talking about finding the derivative of the natural logarithm of x squared plus 1. So the derivative of this is ln of u, is going to be 1 over u, and you see the 1 over u there, times du dx. And du dx is going to be 2x. So that is the answer that we get with u equal x squared plus 1. Here's an example of the product rule. So the first function is x, the second one is ln x. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So that is going to be x. The derivative of the ln of x is 1 over x, plus this is ln of x times 1. And so x times 1 over x is 1, plus natural logarithm of x. And here, what happens is we have even a bigger chain rule. We have here the function on the outside is something being cubed, and the inside function is the natural logarithm of x. So the derivative of this using the chain rule is going to be 3 times this business squared, but then I'm not finished yet because I still have to do the chain rule. So then I'm going to be finding the derivative of the natural logarithm of x, and that is the chain rule, and that gives us 3 ln of x whole squared times 1 over x. you do want to practice these things. Now we're going to expand our scope by talking about what happens if we have something else as the base. So here we're saying the base is not e to the x. The base is a, and the exponent is x. Now, this is a property of exponents and logarithms, that a is equal to e to the ln of a, because those are inverse functions of each other. So you see a to the x is the same thing as e to the ln a, which is a number, times x. So we can use the chain rule here. So you see what we get is it's going to be a to the x times ln of a. Now, if a were e, that would just be 1, but otherwise we will have a constant. So here is the formula that you should know when a is not e. Actually, this formula is true even when a is e. Well, I'm not to the formula. This is your change of base formula. If you wanted to find the logarithm base a of x, this is 1 over the natural logarithm of a times the ln of x. This is something you studied in your pre-calc. And we're going to use this formula also. But you see, what happens is the logarithm to another base is really a constant. Again, this is a constant. It's just a number times the natural logarithm of x. So you see, when I take the derivative here, I will have this as a constant. When I take the derivative with the exponential, I'll have the reciprocal of this as the constant. And in fact, now here's the formula that I was looking for. So you see, when we take the derivative with respect to x of a to the x, this is going to be the natural logarithm of a times a to the x. And when I take the logarithm base a of x and the derivative of that with respect to x, you'll get 1 over ln of a, that's a constant, times x. And if I use the chain rule, what I will be doing is I'll be doing the same thing, except I will be multiplying one more time by du dx. Again, these are formulas you want to have in your toolkit. Okay, so we want to find some derivatives here. So what is the derivative of 2 to the x? Well, that's going to be, this is not e, so that means we have to have this factor of ln2 times 2 to the x. So that's what we get for this derivative. Here, y is equal to 2 to the 3x, so that is going to be ln2, and then this times 2 to the u, but then this is going to be times du dx, which is 3. And so if you put the constants together, 3 is a number and this is a number, so this is 3 ln 2 times 2 to the 3x. It can be a little more complicated, and here I would probably be asking you, we're going to talk about 55 and we're going to talk about 59. A little bit more complicated here, and you can in fact use properties of logarithms. So let's look at these. So the property of the logarithm that we're using here is if y is equal to the logarithm base 5 of this whole thing raised to the 1/2 power, which is what this is, you can bring the 1/2 in front of the logarithm and get this. That makes it easier. So the 1/2 is just going to sit there when I take the derivative. But now we have the logarithm base 5 of u. So this is going to be 1 over u. That will be this one. And the ln 5 is in the denominator from the formula that we knew. And then it's times du dx, which is 2x. And if you simplify that, the 2's will cancel, and you will get this expression. Here is another problem. Again, we'll use properties of logarithms here to make this come out well. So the logarithm base 3 of the quotient is going to be the difference of the log of the numerator minus the log of the denominator. But the logarithm of the numerator, it's a product, so that is going to be the log base 3 of x plus, And now we're using that trick of using the 1/2 there, plus, this is log base 3 of x minus 1, minus the log base 3 of 2. Now everybody please realize that the log base 3 of 2 is a constant. So when I take the derivative, now I just have done pre-calc so far, but when I take the derivative, that's going to be 0. So this one is logarithm base 3 of x. That's going to be 1 over x times ln of 3. This one is going to be 1 over 2, that just sits there, times 1 over x minus 1, but it was log 3, so that is ln of 3. So this is the expression that we have, and if we simplify it, we can have it look like this expression down here, which we might want to do in solving some problems that we will come up against later. Algebra is, of course, your friend. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.